Okay, let's consider another problem about proportions. So, according to equine genetic theory, if we take two red sorrel Appaloosa spotted horses, if you don't know what an Appaloosa spotted horse is, you should look it up because they're kind of neat looking. So if we mate two such horses, there's a 0.75 probability that the foal will also be a red sorrel Appaloosa, and otherwise the baby won't be. It'll not have the spots. So we have a genetic researcher who is analyzing a sample of 200 foals in which both the sire and the dam had this red sorrel Appaloosa pattern, and it turned out that 135 of the babies were red sorrel Appaloosa spotted horses. And so now what we want to do is we want to analyze this sample and to find out if it provides evidence that the proportion of Appaloosa foals from these matings differs from 0.75, and we're given a confidence level of 90%. Okay, so let's get started. So let's start with the sample information. I'm just going to divide up my workspace here. So what's my sample size? 200. My characteristic of interest is the Appaloosa spotting. And so then we want to find out our sample proportion of babies that had this. So our sample proportion is going to be our p hat, which is going to be the ratio of the number of babies with the characteristic of interest divided by the total number in the sample. So x over n. And so for us, this is going to be 135 over 200, which is 0.675. Okay, now we want to see if our assumptions are met. Okay, so for this, what I'm going to do is I'm going to make myself a little table. So these are going to be the babies with spots, and these are going to be the babies without spots. Okay, so how many babies have the spots? 135. How many do not have the spots? We're going to do 200 minus the 135, which is going to give us what? 65. Okay, so both of these are at least 10. And so what that tells us is that tells us that the assumptions are met, which means that p hat follows a normal distribution, which is what we want. What to do for samples that are smaller than that? You would need to take a more advanced statistics class. And so it turns out that if your p, your proportion, is really close to 0 or really close to 1, like maybe if it's 0.03 or 0.97 or even 0.92, you're going to need a much bigger sample size than if your proportion is close to 0.550%. Okay, so now let's write down our hypotheses. Okay, so we have our p, remember, is going to be the proportion of all babies meeting these conditions that have the Appaloosa spots. So much more than in hypothesis tests involving means, with proportions, it's important to carefully define everything. In this case, our characteristic of interest is having Appaloosa spots, and therefore our proportion is the proportion of babies who have that, because every proportion can be rephrased in the negative. In other words, we could have phrased this problem as there is a 0.25 probability that the foal will not have Appaloosa spots. And you could go through and you could do the same problem. And in that case over here, instead of having the 135 in the numerator, you'd have the 65 in there. And you can work through an equivalent problem, and you should end up with the same conclusion. But what you have to be careful of is that you define your characteristic of interest, and therefore your population proportion. You define that up front, and you're careful about it, and you're consistent. If you aren't careful about that, especially depending on how the problem is phrased, you may get mixed up and use perhaps the proportion with spots in one place and the proportion without spots in another place, and then your analysis will not be correct. So it's important to be careful about that. We don't really have to worry about that with means because we usually know what variable we're talking about. Okay, so now let's do our null hypothesis and our alternative hypothesis. Remember the alternative hypothesis, you can either write it as H1 or HA, either is fine. So both of these are going to involve our population proportion P. So now we need to figure out our benchmark. What are we going to be comparing against? So if we read our problem, where's our benchmark? Our benchmark is this 0.75 probability, right? Right here. So that 0.75 is going to be our P0, but here we're going to have it as a number. So this is going to be 0.75. And then for the alternative hypothesis, we need to decide whether we are being steered in some direction or whether it's going to be a two-tailed test. So we look here, we look at the way that our problem is phrased when it's asking us to do our analysis. Does the sample provide evidence that the proportion of Appaloosa spotted foals differs from 0.75? So if you look at that, you see, oh, it differs from, is that steering us in a direction? If it said over 0.75 or under 0.75, then we'd be looking at a one-tailed test. But because it just says different from, now we've got a two-tailed test. So my alternative hypothesis is going to be just P not equal to 0.75. Okay, I'm also going to write my alpha here. So my confidence level is 90%. So my alpha is 0.10, and we can also call that the significance level. And so remember, we get that from taking the 0.90 and subtracting, sorry, we take 1 and we subtract the 0.90. So we've seen that before for sure. Okay. So there's our alpha. And so basically I like to write down here my benchmark. What am I comparing against? My benchmark is P0 equals 0.75. I know we have it up there, but we're going to have formulas that we need to stick P0 into, and so it's kind of helpful if we have it just written down here. You don't want to put P0 up there because P0 means the benchmark. P means the population proportion. So we have to distinguish between those. So we've got that, and then we basically also get the proportion for the complement. And so what's that going to be? 1 minus P0 is then going to be 1 minus 0.75, so 0.25. So we're going to also use that in one of our calculations. So I like to just go ahead and calculate that right here, and that way I can run with it. Okay, so now let's sketch ourselves a picture. So here's my little normal curve. And we look, are we doing a two-tailed test? Yes, we're doing a two-tailed test, so that means half the alpha goes in each tail. So I'm going to put alpha over 2 here, and alpha over 2 is going to be 0.1 over 2, so 0.05. That's going to go here. And then over here we have alpha over 2, also 0.05. So then we write our critical values, which are going to be where the shaded area changes. So this is going to be z.05, and this one is going to be its negative. Okay? So now what we need to do is figure out what those critical values are that I just put on my graph. So I need to find the z value for those. So my area left of z.05 is 0.95. So what I'm going to do is I'm going to look up area equals 0.95 in the table. And let's go do it. You've probably done this recently, but let's just do it again. Looks like I've done it recently because there's 0.9495. So what z value does that correspond to? 1.6. And so then 1.6 over here, and then up there, that'll be 1.64. That's really close. This 9505 is also really close, so that's going to give me 1.65. We are going to be halfway in between. So let's come back. So my area equals 0.4495. It gives me a z-score of 1.64. My area of 0.9505. Sorry, that should be a 9. This gives me a z-score of 1.65. So to get halfway in between, you can average them. I'm going to just write it out, but you can definitely do this in your head. But if you wanted to do it in your calculator, this is how you get the halfway in between part. This is going to give you 1.645. I usually just eyeball it. Eyeballing it is easier if you stick a 0 on there, because then you can say, ooh, what's halfway in between 640 and 650? 645. It becomes more obvious that way. Okay, so that becomes our critical value. So I'm going to come over here to my sketch and put it on here. So here's my 1.645, and then over on this side I get negative 1.645. So keep in mind I've got two critical values here because we have a two-tailed test, but once you have one, it's easy to get the other. Okay, so now what we need to do is we need to calculate our test statistic. So I'm going to have to do some scrolling here. This is easier on paper. Okay. So my first step in calculating a test statistic, what I always do is I always calculate the standard error first, no matter what test I'm doing. It's just my habit. That way I know I'm following the same pattern every time. So for every type of test, you have a different way of calculating the standard error, but the general approach is the same. So my standard error here, which I'm going to represent sigma p hat. So this means the standard deviation of the set of all possible sample proportions p hat. So this is going to be equal to the square root of p times 1 minus p all over n. But hey, we don't know what p. We don't know the population proportion. That's what we're doing a hypothesis test for. So instead of that, what we're going to do is we are going to put in our benchmark here. Okay, so a very common mistake in this part of the problem is to use your sample proportion. And I know why it happens. It's because that's what we did on confidence intervals. But that's not what we do here. We don't have exactly the same relationship between confidence intervals and the corresponding hypothesis test with proportions as we do with means. And that's because of the proportion actually affecting the standard error, which in a test of means, the population mean doesn't affect the standard error. Okay, so we want to put our benchmark in here. So what is our benchmark? So we're going to go back to where I wrote down my hypotheses. So this is that 0.75. And notice I also wrote down the corresponding proportion for the complement, and because I knew I was going to need that 1 minus P0 later, so I get 0.75 and 0.25. Okay, I don't like to put parentheses in things like square roots. I prefer to just calculate them separately. There's too much chance of putting something into your calculator wrong. So I'm going to do my 0.75 times my 0.25, and then I'm going to divide by my sample size, which is 200. And I'm going to calculate this in my calculator, and I end up with 0.03. I'm going to write out a bunch of decimal places here. I don't retype these. What I would do is I would store this in a variable in my calculator or in the memory recall of my calculator, depending on what kind of calculator I have. And then I can retrieve it later. Okay, so now what I need to do is I need to do my test statistic. So remember the overall pattern for doing your test statistic. What do we do every time? We subtract what we're comparing, and then we divide by the standard error. So in our case, what are we comparing? We're comparing the sample proportion to the benchmark proportion. So that's going to be p hat minus p0. We're going to divide by the standard error. I'm just going to write sigma p hat here, but I'm going to use the value I've already calculated. Okay, so what was my p hat? It's been a while, so let's go look. So my p hat was 0.675. And then my benchmark is going to be what? 0.75. And if those are super far apart, it's not impossible. But then I start questioning if maybe I did something wrong and I got things backwards, like is the P the proportion of the horses with spots or the proportion without? Because if they're really far from each other, that would be unusual. And so I just always want to double check that I've got them both the characteristic of interest and the population proportion set up consistently. So if I liked, I could have done them both for the non-spotted horses instead, and then I'd have 0.25 for the benchmark, and I'd have 65 here in my numerator, and then we would still be fine. Okay, so, but you have to be consistent. So, but I don't see any red flags here. So it looks like my p hat is 0.75 and my benchmark is 0.75. Sorry, my p, yeah, 675 and 75. So then I'm going to divide by, this is that same number, but I'm not retyping it in my calculator because that's just asking for a button punching mistake. Plus, if you round, you lose information. So I'm going to use my stored value. And so this gives me about negative 2.4495. You can also do 0.675 minus 0.75 and then divide by your previous answer. That's another option too. So that also works as long as you don't do anything else in between. Okay, so now we need to go put this negative 2.4495 onto my picture. So I come back up here. Negative 2.4495, that's going to be way over here somewhere, right? Okay, so that's right there. And so now we need to write our conclusion. Okay, so that Z turned out to be in the rejection region, right? So we are going to reject H0. Okay, we're not going to be satisfied just writing that. We also need to say what's actually going on with the horses. So you may want to go back and reread the problem, or at least reread your H0. So my H0 was that the population proportion was 0.75. So now I'm rejecting that, which is going to bump me over to the H1, the alternative hypothesis, which is that the population proportion is not 0.75. So we can say that this sample provides evidence that the proportion of Appaloosa spotted babies differs from 0.75. So we have not proven for sure that the geneticists are wrong with their 0.75, but we have said that at least based on the sample, maybe we just got a weird or a fluky sample that had a lower than expected number of spotted babies. That's possible, even if the population proportion is 0.75. But if we did this a whole bunch of times for a bunch of different samples, that, and if the geneticists were really correct about the 0.75, then only about 10% of those samples should result in a rejection of the H0. Okay, so I hope this helps you understand how to do a hypothesis test for one proportion. Keep practicing, and I will see you next time.